Okay, so thank you very much for inviting me. It is my pleasure to have been invited and to be part in some way of the doctoral network that you are. I find it a fantastic network, and the theme is amazing. So I am, as Luigi said, I am a senior lecturer at the University of Strathclyde in Glasgow, and I'm also a member of the Centre for Ultrasonic Engineering. This is us. This is my team. This is Peter Lukacs. Let me just see if you should be able to see the laser pointer. So this is Peter Lukacs, Gio Davis, and Dawn Pieris, who are the researchers in my team, and Alan Kinnan, Panos Kamingis, Matthew Riding, and Ahmed Alfawairas, who are PhD students. And all of us are doing something that is related with laser ultrasound arrays, which is the topic of this talk. Because of this, I have asked some of these people to actually present their own work to you, because I think it is a great opportunity to give them the chance to actually present what they're doing. So I've asked Dawn, who is going to present a automation of laser-induced phased arrays for industrial applications and how this can be implemented using robotics. And then Peter Lukacs is going to be giving you a talk about how to image in 3D using 2D laser-induced phased arrays. And then Matthew Riding is going to give a presentation of how to measure both thickness and ultrasonic speed using laser arrays. Then I'll have the pleasure of presenting the work of Gio Davis, who unfortunately can't be here with us today, on crack detection on thin-walled cylindrical steel rods. So it's because we have planned so many things, I encourage people to participate. I find that a lot of the things that we're going to be presenting to you have a lot of common themes with the topics that you will be doing, you currently do, or you will be doing in your PhDs. So please participate with questions. So I will be more than happy to hear you interrupting me and asking questions while I'll go on with the presentation. And also, if you want, you can always take notes and ask in the end. Okay, so as I said at the beginning, I suggest that we take a 5-minute break after my talk, just to break and stretch our legs and break the long stretch of presentations. So the title of my work, of the part that I will be presenting, is Adaptive Laser-Induced Phased Arrays. I know that some of you may be doing laser ultrasound, most of you do not, but what I want you to take away with you from this talk is that there is an alternative way of thinking about ultrasonic phased array imaging. So, I will be talking about this in the following slides. But first of all, I'd like to show you where we are. We are at the University of Strathclyde, which is located in Glasgow, which is in Scotland. Glasgow is here, and we are right at the heart of the city of Glasgow. Our campus is the main square in Glasgow is here, that green square that you see here, and the campus is next to it. I am here in George Street. The building that I am at the moment is called Royal College, and inside this building are the labs. So we have the sensor-enabled automation, robotics, and control hub, which you see here. It is located in the Royal College, and inside the lab are all these labs that you see here. A lot of robotics, a lot of ultrasonics, and in this lab, we have the remote ultrasonics and laser-enabled sensing, which we call ourselves RULES. So this is who we are. So I'm going to move on to the presentation. I'm going to be focusing on our activities on non-destructive evaluation, NDE. So within this field, the question is, why laser ultrasonics for NDE? And the thing is that the current and future challenges of advanced materials and processes push the limits of NDE to extreme. And we're constantly asked to do inspections in hot, hazardous, extreme environments, places of restricted access. We're called to inspect complex geometries, and we're faced with contamination issues where the presence of couplant or touching or contact with whatever it is that we are inspecting is completely out of the question. That's where laser ultrasounds, ultrasonics come into the scene. It is a completely remote and couplant-free technique. It is wireless. It has a small footprint. It has minimal impact. It's just basically laser beams on a component, and it can be fiber coupled to address places of restricted access. Now, the thing is that with conventional laser ultrasonics, the challenge is the low signal to noise ratio, that it is because we want to stay at the non-destructive regime. So, and I will give you some examples of what we call, or what I mean by low signal to noise ratio. And because of this low signal to noise ratio, we paired laser ultrasonics with phased arrays. We did this by introducing advanced data acquisition methods. And in this case, we're talking about full matrix capture and advanced imaging algorithms like the total focusing method. I don't know how many of you are familiar with this, so I'm going to introduce them in the next slides. So by doing this, by introducing these advanced methods for ultrasonics into laser ultrasonics, we can have high resolution ultrasonic images. Now, these are some of the topics that my team is addressing currently and what I would like to address in the future. So we're talking about applications, and what we do is use laser ultrasonics for in-process inspections, for example, additive manufacturing, ultrasound tomography for metallurgy, in situ inspections, for example, NDT in power generation, nuclear fission and fusion, thin inspections in thin structures, and medical imaging, for example, biomedical ultrasound tomography. And the people that are involved in these areas are shown here, and this slide actually shows the areas that are active within the team at the moment. And you're going to be hearing about these applications when they will speak. So going back to the topic of my talk, which is phased arrays. Okay, so ultrasound is a powerful, and it is relatively a very safe technique, which we have made it the most common imaging modality to image anything that lies below the surface. And this is both from the medical and the industrial world. And the reason why imaging, ultrasonic imaging has become so successful is because of the instrumentation that has been developed. The phased arrays are at the heart of all the successes that ultrasonic imaging has achieved. And we're talking about transducer elements, the sensors themselves, the electronics, the data acquisition processes, and the imaging. All of these development have caused this revolution of phased arrays. But the instrumentation, the influence of the instrumentation is so strong that if I ask you now to imagine what a phased array is, the image that will pop into your minds probably has something like that. And the thing is that this is such a strong influence that the capabilities and the limitations of the phased arrays, of these transducer-based phased arrays, have come to define what we can or cannot do in phased array imaging. And in particular, the data acquisition, the imaging algorithms, and everything else that is being developed is actually developed for transducer-based phased arrays. And so within this talk, the question is, how would phased array imaging be different if we didn't have the current limitations that the transducer-based phased arrays have? So this is an alternative way of thinking about phased array imaging. Okay, so before going to the alternative way, we need to just review quickly what transducer phased array imaging is. So the phased arrays are rows of transducers that are able both to generate and detect ultrasound. And we apply the appropriate time delay between the elements, and we steer and focus the ultrasound to image, take the capture the signals and image what it is inside. So these are some common strategies of doing phased array imaging. That was swept B-scan, the focus swept B-scan, and you have the section B-scan. And all these strategies, the transducer phased array has a fixed number of elements, who have a fixed position, who have a fixed pitch, they have fixed operational frequency, and they have fixed corresponding bandwidth. So all these are the characteristics of the transducer phased array. What if we didn't have these constraints about the phased array? How would our phased array imaging look like if we didn't have these? So while you're thinking about it, I'm going to introduce how we are making laser ultrasound phased arrays by taking you straight on to our experimental setup before even attempting to explain to you how we generate and detect ultrasound. So this is the experimental setup, and the sample is sitting here. And there is no couplant. And the lasers who are generating ultrasound and detect ultrasound stand here. So this is a generation laser, and you see that red beam that we have drawn, and the beam path. And this is the detection laser, which is a rough surface interferometer, and it sits usually at the working distance between 200 millimeters or 100 millimeters, that just simply because these are the working distances that are convenient for us. Both of these instrumentation are able to scan the laser beams. We are doing the generation laser scanning by using this scanning galvanometer mirror. It's a combination of two mirrors, and this is able to scan the beams both left and right and up and down. And the same with the detection laser. It sits on linear stages, which are able to move it left and right or up and down. And so we go to the question of how do we generate and how do we detect ultrasound using lasers. You need a pulse laser to begin with that is focused onto the surface of the sample, and very locally and very fast, we're talking nanosecond, it heats a small amount of that component, the surface of that component. And this heating causes it to expand. It's thermal heating, and it has a thermoelastic expansion which pushes away the surrounding material, causing the appearance of the ultrasonic waves. All sorts of waves are excited at the same time. You see in this low tech video that cartoon that both surface waves and bulk waves are present, and we have both longitudinal and shear waves as a generation. And for the detection, we have a second laser. It is an interferometer that is able to detect out-of-plane displacement. And for out-of-plane displacement, these are the directivity patterns. So for the longitudinal, we have the omnidirectional detection pattern. And for the shear, you see this has these weird lobes. Yeah, going back to the generation pattern, you see that the longitudinal has these lobes at around 6 degrees, and you see that the shear has these very focused lobes at around 30 degrees. It's not only that, the story doesn't end there. The shear wave at the thermoelastic non-destructive regime, the shear wave is excited much more prominently than the longitudinal. So you see that, in fact, 10 times more energy is directed to the generation of the shear wave than the longitudinal with laser ultrasound. So we're going to the more theoretical part of how laser ultrasound is generated, and you see here a finite element simulation of a wave that, well, all the waves that have been generated using a laser. And you see this is the wavefront from the longitudinal wave, and you see the wavefront is strong at around 60 degrees. And you see the wavefront of the shear wave, which is shown here, and the wavefront is located and focused around 30 degrees. And you also see that it's much more pronounced in amplitude. The surface acoustic wave is here. The surface scheming longitudinal wave is right at the interface between the surface and the wavefront of the longitudinal wave, as it should be. And this is an experimental waveform, and it shows the arrival of these waves. Okay, so it's time versus amplitude, and you see all these waves: the surface scheming one, the surface acoustic wave with a huge amplitude, orders of magnitude above the others, longitudinal, shear, and here is the mode converted wave. Okay, you see it, and this is experimental, and the interesting part about it is how low the noise is, and the reason why it is so low is because it's 4,000 averages. If I show you what the waveform looks like at a number of averages, which is more closer to what we are doing experimentally with 100 averages, anything that is not the surface acoustic wave is being drowned in noise. That's why we use phased arrays. So if we are trying to do imaging with that, and we're going for a B scan, which is the conventional way of looking at ultrasound, this is what we get. This is the image that we get. This is the surface acoustic wave. This is the surface scheming longitudinal. And below the surface, that's the longitudinal arrival. And the curve is now fainting in the background. This is the mode converted one, and this is the shear wave. That's 4,000 averages, and that's not industry relevant. If we go to something that is more industry appropriate, then we see that most of these arrivals have been drowned to below the noise level. You can just about see the mode converted wave at particular angles, and the same goes with the shear wave. So I'm now going to get into the phased array imaging as opposed to plain laser ultrasonics. And I'm just going back to the general ultrasonic phased array imaging. And I'm going to be talking about a particular data acquisition method, which is called the full matrix capture in the NDE world. It's called also synthetic aperture in the medical world. And what is particular about the full matrix capture is, first of all, that the focusing is done in post-processing. And also, the second most important part about it is that it is the method of capturing the complete, the most amount of information. And this is a data acquisition, and the way that it works is that we collect all the data from all the possible combinations between generation and detection. And this is done from the elements of the array. In the transducer arrays, this is done by having one element generating ultrasound and all the other elements receiving ultrasound. So how does this look with laser-induced phased arrays, or as we call them, LIPAs? Okay, so we have one laser beam that generates ultrasound. It is marked here as red, and one laser beam that detects ultrasound, and it's marked here as green. And we start scanning each one of them with where we want the element location to be. And then this moves, sorry, this went a bit too fast. Yeah, so the second beam moves to a second element location, and the process starts again, and so on until all the possible combinations have been captured. You have to see that straight away. First of all, the first thing that you see is that the generation and the detection mechanisms are completely decoupled when we're talking about LIPAs. And that brings a lot of flexibility in array design, a flexibility that you cannot have most of the times in the transducers. And the second thing is that now the definitions of the location of an element, or how many elements you have, or where are they, how they're distributed, it completely takes a completely new meaning. So this is about flexibility that we can have with LIPAs that we cannot most of the times have with transducers. So this is what a scan, a full matrix data acquisition looks in practice. So this is the inspection of a pipe And you see the red beam scanning and the green from the generation and the green beam moving and following along. And we can do this in 1D, synthesizing 1D LIPAs for 2D ultrasonic imaging. And we can do this in 2D for 2D LIPAs for 3D ultrasonic imaging. And this is what they look like. Regarding the imaging algorithms, I talked about using the total focusing method, which is a delay in sum algorithm. And it looks like that. So we collect all the data, and then in post-processing, at each point in our imaging plane, we take all the data with the appropriate time delay, which is applied in post-processing, and we sum them. So it's a delay and sum algorithm. And with this, in this case, there is a focusing at each point in the imaging plane, and that gives us a really high quality ultrasonic image. What you see here, it is an experimental image from a titanium alloy with all optical data. And what you see here is down to 15 millimeters below the surface of the sample, imaging 1 millimeter sidereal holes. So the advantages of capturing the full matrix is that we get high quality ultrasonic images, as you see. And also there is a wide range of post-processing algorithms that we can apply to the same data sets in order to improve and enhance our imaging. The downside is that there is slow data acquisition, and also we end up with really large data volumes. And if you're doing ultrasonic imaging, phase array imaging using transducers, you probably don't understand what I'm talking about with slow data acquisition, because you just put your array there and instantaneously, almost instantaneously, you have your data. But that's not the case, even for lasers, but even for transducers, it's not the case when we're going to introduce 3D imaging, because then the data acquisition takes time, and the data volumes do become extremely large. So one of the techniques that have been proposed to improve these conditions, these issues, are to introduce array sparsity. Now, how do we do this, and what do we mean by array sparsity? Up until now, we have been talking about full matrix capture, right? And we are considering what is called a dense array, and it is an array that conforms to the Nyquist sampling criterion. The Nyquist sampling criterion says that the pitch of the array should be at least lambda over 2, where lambda is the acoustic the ultrasonic wavelength. So if the pitch is larger than this limit, then the waves cannot be resolved spatially. So this is for a full matrix, so for a dense array. However, if we're going to sparsity, we remove some of the elements, and now that condition is no longer valid, because the pitch is now bigger than lambda over 2. And there are some array designs that have been proposed to deal with sparsity. The first one is a periodic array equidistant element spacing. Another one is a non-periodic but non-deterministic. This means that, for example, a random array falls under this category. And another one is a non-periodic but deterministic, which means that the pitch between the elements is not equal, but it varies according to a function or something else. These were for 1D array designs. For 2D array designs, we can have, these are the equivalents. So for periodic, we have matrix array. Non-periodic, non-deterministics are the random arrays. And an example of non-periodic deterministic for 2D is a spiral array. The problem that all these 1D array designs are trying to address is grating lobes, because as soon as we go to sparsity, as soon as we introduce sparsity into the array design, we have to deal with grating lobes. So certain sparse array designs can help improve sampling. What do I mean by grating lobes? So these are the effects of the grating lobes, and this matrix array is shown here, and this is the directivity of this array when it tries to focus at the center of this plane. And you see that the energy is not all going to the center. There is a lot of energy that is distributed in those grating lobes. This is a vernier array, so this is a different array design, and it's a particular array design because it has a different array design for the detection array and a different design for the generation array. So the generation array is marked by these red dots, and the detection array is marked by these green dots. And they are equidistant, both of them, but they have a different pitch for each one. And you see that they are a little bit, this particular design is a bit better at dealing with grating lobes and has suppressed a lot of them, but they're still there. The random array, where again the elements are the elements for the generation and detection in this particular design are the same, but they are distributed randomly throughout the aperture. The random array again is focusing in the center, and now there is a much better suppression of the grating lobes. Peter Lukács is going to talk about the effects of grating lobes and the 3D imaging in his talk later on, so stay tuned. In the meantime, I'm going to be focusing on the full matrix capture and what we mean about capturing the maximum information that we can with this array, because indeed this full matrix capture does that. But the problem is that this information is dictated by the location of the region of interest. So in these points here, in these graphs, the region of interest is shown as a red circle. The thing is that the full matrix capture would capture all the signals from all of these elements. But depending on where that that region of interest is located, there are a lot of elements that will not have information. They will only contribute to noise. And there are only a few elements that could contribute to signal. In this case, we've marked the elements that contribute to signal with green. And this is the case for that region of interest when we are trying to image using a transducer array, and the transducer directivity is shown here. This is the case when we are trying to image using a laser ultrasound with the shear mode, and the directivity is shown here. And this is what the information from the elements would look like in this case. And in this case, it's an EMAT, an electromagnetic acoustic transducer. And this is the directivity pattern for longitudinals for this EMAT. And these are the elements that would contribute to signal and the ones that would not. So the question is, could we have a data acquisition that would not capture all the ones that all the signals that do not have information, but would only capture the signals that have information? So we're talking about an adaptive data acquisition method. This is what we're trying to do. We call this a selective matrix capture, and it is an adaptive data acquisition. And in this case, the array design is adapted on the fly according to the presence and location of internal features and the capabilities of the imaging system. So the array design depends on the presence and location of internal features and the capabilities of the ultrasonic imaging system. And this is explained with this graph here. This is the combined sensitivity of the generation elements and the detection elements of a 90-element array, in this case, a laser-induced phased array, and for a region of interest that is at the center of the array. And what you see is that the information, the elements that would be around the 20th element of the array and around the 70th element of the array would, of the generation array, would have information. And the ones for the detection that would have information would be at around 10 and around 80 here. All the others would contribute mostly to noise. So let's see how this is a flow chart of how this selective matrix capture would look like if we try to implement it. So we start by synthesizing a sparse array. We don't know where there is a region of interest or if there is a region of interest at all. So we just distribute the elements equidistantly, well, in a specific strategy, but without any knowledge, and it is a sparse array. And then we do this iteratively, adding elements as we go, gathering information, doing the imaging, and we look at the images until we have enough confidence to say that there is no region of interest at all, at which points we finish the scan after a quick data acquisition, or that there is a region of interest and we end up with a low resolution image. But the important information is that this low resolution image gives us the location of the region of interest. This is a stage 1 of the detection and localization. And then we move on to stage 2, which is the array optimization and characterization. And now we know the location of interest, and we know we design an optimized array tailored to that location of interest. And with this technique, we end up with a high resolution image and end the scan there. So it is a reconfigurable array, an optimized array that we are doing. What we want to do is automate the whole process and not have someone to do manually and look at where or the region of interest is or when to switch from stage 1 to stage 2. And to do this, we need to introduce a criterion that will take us from stage 1 to stage 2. There are lots of ways that you can introduce this criterion. An example is the straightforward amplitude threshold implementation that most of the NDE are very familiar with. So you just put an amplitude threshold, and once in your images this threshold is exceeded, you call it a region of interest. Another way of introducing that criterion would be with machine learning. So you train a network to see the images and recognize the appearance of these regions of interest, which would be a coherent signal as opposed to the random noise surrounding it. What I'm going to show you today is a new method of a new criterion that we have come up with, and it is a very simple kind of criterion, and we call it a noise distribution of the intensity pixels, of the pixels intensity. And this is shown here, and it's based on so what is monitored is the pixels intensity on that TFM image, on that ultrasonic image. And the idea is that since our noise is random, then if there is no coherent signal present, then that noise distribution should be random. It should have the characteristic random distribution, which is shown as like this bell curve here. However, when there is a region of interest, when there is a scatter, a coherent signal, then it should be signaled by this pixel intensity distribution, because these pixels would now push the random noise distribution to higher intensity bins. So then the scatter is actually here, and the noise is still there. We are just, because the noise is predominant we are monitoring the shift. So the blue and yellow curves here contribute to, the blue curve here is showing the noise distribution for the case of no scatter, and the blue and the orange curves here are corresponding to these images with the scatter, and they are with or without normalization. This is with their normalization to the highest point in the image, which is the scatterer point in this case. And this one is without the normalization, in which case we don't have a shift, but we have the appearance of the pixels from the scatter at below the 0. Okay, so that's the criterion for taking us from stage 1 to stage 2. And the question now is, okay, so we know the location of the scatter. How can we optimize our array? What kind of array design would we choose? And I'm showing you here two different strategies of deciding what that array should look like. The first one, we call it the surface projection threshold. And what we do is we take the generation directivity and the detection directivity patterns, these lobes that I was showing you before, and we project them to the surface because the surface is where the elements of the array are located. And we end up with these curves that you see. So the red one is the projected generation directivity, and the green one is the projected detection sensitivity. And what we do then is apply a threshold. I've put 50% drop, but it could be anything that works in practice. And what we do is that anything that is above this threshold, any area, this will be determining the aperture. So the boundaries of that threshold will determine the aperture of the array. And within this aperture, we go for an equidistant array and a dense array. So the pitch will be decided by the frequency that we want to observe. So this is for the generation, and for the detection, we do the same. We have the aperture dictated by the threshold, and then we go for an equidistant distribution. So this is one optimization strategy that will leave us with the elements that will have the most information. There will be most information reach. So we're going for the highest signal to noise ratio in this case. Another strategy is the sensitivity-based element distribution. So the sensitivity-based element distribution distributes the elements throughout the aperture, the available aperture, but the distribution between the elements differs according to the area under the curve. So we have the curves from the generation directivity and detection sensitivity, and then we divide them according to the area under the curve, the integral of these curves. And so that means that in areas where the directivity is higher, it is maximized, then the density of these lines becomes higher. And that means the distribution of the elements, which is at the edges of these areas, are going to be more dense. So we end up with this type of array for the generation and detection. As you see, there are different arrays for the generation and different for the detection. The advantage of over the previous strategy that I just showed you, the threshold one, is that now we have a few elements that are getting information from different viewing angles, from wider viewing angles. And although there isn't much there, there is some information there. And this is useful. And you will see what I mean in the case study. So this is a case study that I bring to you for implementing this technique, this SMC. We go for a simple aluminium block with a side drill hole of 1 millimeter diameter located 15 millimeters down from the surface. And we do the stage one. We are synthesizing arrays iteratively on a 30 millimeter aperture. And we go for the first round with 10 elements only and very sparse array, 3 millimeters pitch. And we don't see anything above the noise. And this is shown with the blue curve here, which starts at 0 and is going nowhere. No elements again, sorry, the number of elements now is increased to 15. The pitch is going to 2 millimeters. And again, we get the red curve, which doesn't change from the blue curve. When we go to 30 elements and the pitch reduces to 1 millimeter, now we have a shift, a clear shift in here. We can see this in the TFM as the appearance of the region of interest is shown, and the shift is there. So as soon as we have the shift, we go on to stage 2. And these images show the different arrays. All of them have an array aperture of 30 millimeters, but the array design is different. In this one here is the classic FMC with 193 elements and 0.155 millimeter pitch, a dense array, and it looks like that. And this is our standard. This is the best SNR that we can get as far as we can see it. This is a sparse but equidistant array. So we assume that here we don't use the information about where the location of the region of interest is. We just distribute the elements, 46 elements, with a 0.650 millimeter pitch, and we get that, which has a much worse signal to noise ratio. If we go for the first strategy of the sensitivity, the threshold approach on the distribution of the elements, we get this picture here. Again, 46 elements with 0.155 millimeter pitch, a dense array where the array is synthesized. And here is the sensitivity based distribution with 46 elements with varying pitch. And you see what we have here. The signal to noise ratio is lower, but if you look at the zoomed up images of what the defect looks like, you see something like that. So the FMC is shown here, the sparse equidistant. The SPT, the threshold one, is showing the signal to noise ratio is very good, but compared to the SMC, so to the FMC, the imaging characteristics are slightly deteriorated. Whereas if you look at the SED, the characterization of that defect is as close to the FMC as we can get it. But here's the comparison. This is the downline. Why are we doing this? The number of signals that we need to capture with the FMC is close to 37,000. Was with a sparse, with all the rest, all these other arrays, is 2,000. Is only 2,000 signals. The SNR that we can achieve with the FMC, 65 dBs. The SNR of the sparse equidistance, so no information about where the location of the array is given to the design of this array, is down to 40 dBs. And whereas the threshold design of this array brings the SNR to 65 dBs, just as good and slightly above than that of the FMC. With the SED, with the sensitivity-based distribution, we go to 50 dBs, slightly lower, but then we have a little bit better of characterization. The scan time for this is 42 minutes. The scan time for just doing the stage 2 is actually 2.5 minutes. Here in these two, we have included stage 1. So the total of the whole SMC is 4 minutes in these two. So a huge difference between the scan time of the full FMC and the optimized designs. And there's the other knockout effect is on the data size. For the FMC, we needed to capture 97 megabytes, whereas in the optimized arrays, we could get away with just 9 megabytes in total, both for stage 1 and stage 2. So that's it for me, almost. So what I have shown you is an adaptive data acquisition method, which we call SMC. I've shown you that this method, we don't need to know where the location of the array is where the location of the region of interest is at the beginning, but we build up the knowledge as the scanning goes, as the data acquisition is built up. The array optimization is done during the data acquisition. So on the fly, the array is changing. And it is as efficient as the SMC, as the FMC. We see that with one strategy of array optimization, we get as good a signal to noise ratio as the FMC, and even actually is slightly better than the FMC. And with the other optimized array, we get similar scanning resolving capabilities. It is faster and less data volume is collected. We have 17.5 times fewer signals that are collected, but these signals have all the information that we need. It's 10 times faster, and it gives 11 times less data volume. Underlying all this, I hope, that was my initial hope, to have introduced some imagination into what phased array imaging can do outside the boundaries of the transducer phased arrays. So it is a flexible way to synthesize arrays. It is an alternative way of thinking about phased array imaging. In the future, or some of these are actually being done as we speak, we want to do multimode imaging. We want to introduce other criteria that will take us from stage 1 to stage 2, and we want to do automation. And a lot of these is being implemented for volumetric imaging, for 3D imaging. So that's us. And I know that you're doing your PhD, but if you know other people that are dreaming about doing PhD and are interested in this research field, so please get them to contact us. Any questions?
Yes. No. Can you see me today?
Also, almost. I am not as fast as that, so I need to switch. Yes, now I can see you.
Okay, my name is Damiano, and what impressed me and interested me the most, it's this, let's say, two-stage process that you described of first identifying the ROI, location of interest, and then once we know for sure that there's something that interests us, to have a more fast and more detailed acquisition on that stage. And I was wondering, before you mentioned one technique would be to have a classification of the region of interest using machine learning methodologies, or let's say data-driven methodologies. And it's something I was wondering, is this task do through like supervised methodologies, or you can get away with unsupervised methodologies that can refer to?
I think I will leave it up to you.
Okay.
We're in the process of developing the criteria ourselves. We had a go with machine learning through a master's project, and we were using supervised learning while we were training the network, and then unsupervised machine learning application.
Okay.
So that was our approach, which was, as I said, a very quick project that happened over a summer. But yeah, it's a very interesting way of application for machine learning, I think, characterization of region of interest. Any other questions?
Yes, I have one. Thank you very much, Théodosia, for this very interesting presentation. So I'm Odile Abraham, and I'm working in civil engineering. And we design a small scanner using a laser as a receiver, but a contact source. And so now you are speaking about laser. And I wonder if there is some outdoor industrial application of this, because it's really challenging, I guess, to have such an equipment working on site. And I'd like to know if some devices exist with maybe less high resolution, high power on site, so that you can move the device and do some measurements, laser measurements.
You're talking about detection of ultrasound, right?
No, the full system, laser on site.
So I am not the expert on civil engineering applications of lasers or ultrasound.
No, but
I think there are. Sorry.
Sorry. Yes, in engineering it doesn't exist, but in other fields maybe.
Oh yes. Oh yes. Something that is in the industry, and it's been in the industry for about 20 years, more than 20 years now, is during manufacturing of metal builds. So in metal farms. Sorry.
Yeah. Okay.
Whereas there's hot metal and they want to measure the thickness of the rods or the rails that they are manufacturing, they're using laser ultrasound because they want to know the thickness, and this is probably the only way that they can check what it is with ultrasound when the material is at thousands of degrees hot.
But the equipment is in the factory, and the equipment
is in the factory. It's on steel mills, and they're doing this in situ, and they've been doing this for 20 years. So this is one application. Another application, there is at least one system, laser ultrasound system, commercially available for the inspection of composites for aerospace applications. There's laser ultrasound microelectronics, where they're using ultrasound to check for the chips for the electrical integrated circuits. This is NDT, this is condition, and they just want information about what's going inside, and they don't want it with couplant because it's chips and they're electronics, and they're very particular about the contamination with water.
My question was about an experimental setup that you can take with you in your truck or in your car and move from one place to another. So it's
a portable one. So you're talking about a portable ultrasound?
Yes, I mean something that you can use outside, because yes,
I don't know of any others that are not experimental or research based. I take my lasers sometimes outside, and I do experiments in situ. But it's not a commercial system, if that's what you're asking for. Yes, and I know Dawn, who's going to be speaking just after me, he wants to take the lasers out and put them in an additive manufacturing environment just to show, and he's going to also be showing you how he's doing this with robots, with putting them on a robotic system.
Oh, great. That was my question. Okay, cool. Thank you very much.
Hello, madam. I have a question. I understand how the laser interacts with the material, and then the material can produce some ultrasonic waves. But I don't really understand how the ultrasonic waves can be detected by the laser, by the detector.
Okay. So it is an interferometer. So, which means that it uses the particular one that we are using. It uses a signal beam. So the beam is split into two parts. The two parts are not equal in that case. There's only a small part that is used for a reference, and the other part is used for the signal. The idea of the interferometer is to be able to detect the phase difference, the phase of light. So instead of amplitude, we have to translate somehow the phase of light into amplitude modulation, and that's what the interferometer does. So by using two beams who have traveled, they have traveled similar paths, but they have not reached the same conditions at the end. One of them, the reference beam, has a mirror-like surface. The other one is the moving surface. Okay, so this is the part that receives the ultrasound and is moving. It's and that movement, that modulation is the one that we are detecting. So at the end, we are receiving both beams, both the reference and the signal, and we ask for them to interfere. So we put them into an area. Well, in this case, it's our detector at the other end, a photodiode or photodiode detectors, and because of the interference, they will have the phase difference between them. They will have bright regions and dark regions. So the movement of the displacement because of the ultrasound will cause a movement, a modulation in the fringes of that interference pattern, which the photodiode will detect. And that's how we detect the movement, the displacement.
Yeah, I understand the principle of interferometer, but do you need to adjust the angle of the photodetector to align the laser source with the photodetector?
Not in the particular interferometer, because we're using a rough surface interferometer. It's a commercially available interferometer. It's from Sound and Bright, and it's called the Quartet. Okay. And what it does, it works with speckles. It's a speckled interferometry. And how does it work? The problem is that in the phase of the speckle is random. So it's a random phase one. What they do is they gather all the speckles, or as many speckles as they can from the wide angle reflection of the laser beam, which is why you see this big optic. You still see my screen, right?
Yeah.
So you see there is a large optic at the end, which is a large lens that's trying to gather as much light as it's coming from the surface. And with the rough surface, there's a lot of scattered light, which is what this one has. And at the other end, their detector is quite particular. Instead of having just one detector, they have an array of detectors. It's a 2D array of detectors, and they throw both the reference beam and the scattered beam from the surface. And this array, at each element of this array, it becomes an interferometer. So each speckle interferes with a portion of the reflection of the reference beam. That's how this one works.
Okay, thank you.
Yes, I have another question regarding the excitation using the laser. As of right now, it's only basically you can only use it on isotropic homogeneous materials like metals, right? Rather than like in composites or such.
No, that's not true. Lasers have been used. Laser ultrasound has been used with composites, and it was actually one of the early implementations of laser ultrasound. And the reason for that is the complex shape of composites, which the transducers find very hard to accommodate. So you use composites to make complex shapes, but then you have to inspect them with ultrasound, and you don't have the transducers to do it. So,
right.
Yes.
But how do you exactly model how the waves are created by heating, let's say, a composite or something like that?
It is still the directivity patterns are completely different in composites, because the directivity patterns that I presented would be more valid in metals, and the ones that I presented are only for aluminium, for example. In composites, you have completely different directivity patterns, but they're still directivity patterns, and energy does propagate through the composite. It is anisotropic, and the energy will go in a funny way, in a funny place that you don't expect, but it's still there.
All right.
That would happen with ultrasound anyway. I mean, even with transducers, if you excite them, the ultrasonic energy is going to be following its own anisotropic path. So the same way.
All right. Do you have like a library or something where you could find out these patterns, or how do you determine these?
You make them, you simulate them, and they are different for each material. You put the elastic properties of the material, and you simulate them. There are lots of software like COMSOL who will help you to do that.
Right. And also thermal properties, right?
Yeah, and lots of people have already done this, so you can look them up in the literature.
Yeah, sure.
Okay. So, Luigi?
Yes, of course. Okay, I will go to number 24, which probably is not number 24. Is this one? Okay. Yeah, I think I understand your question. This is an exaggerated picture to show the problem. And the problem, and the underlying problem, is the fact that we do not know where the region of interest is. And we have to collect the data agnostically. So without any knowledge where the information comes from. So we take everything, and a lot of this everything is noise. And we end up with a lot of data that is noise, and then we don't have we have only a few data that is information. So if your question is, This is the transducer directivity. If the question is, why does the directivity look like that? Is that your question? This one. They are different. Well, these are different transduction mechanisms, and each one of them, because it says longitudinal and longitudinal. Is that what okay. This is a transducer, okay? And this is an electromagnetic acoustic transducer. There are different things. So the completely different transduction mechanisms. This is a piezoelectric element. This is an electromagnetic transducer. So it is a coil that is wound in a pattern. And because of that, they have completely different directivities, even though it's longitudinal waves. The laser ultrasound also has its own directivity for longitudinals, which is completely different from each one. So the answer is they're different because they are different mechanisms of generating ultrasound. No, the green points. Oh, sorry. There's no correlation between the points on the surface, the color of the points of the surface, or the color of the region of interest. That's a good point. We need to change the colors. No.
I think I see it, Teti. I'm sorry. I think I see what Marios is asking. If I may, just there, you're talking about the circles on the top of the drawing. Teti, just to take your comment to the circles, the coloured small circles, which are the array locations on the surface. They have been coloured either grey or green. And the ones which are coloured green are the ones where if you put a laser there, it will release a wave that will travel towards the red target. And so we call this good directivity, high directivity. But you see in the case of the final grey sample, the lowest one, the bottom one for the EMAT, there are five circles in the center of the array which are colored grey. This was your question. They do not provide directivity to the defect directly below them because the emission is at an angle. And so it does not emit the sound straight down. It's okay? The red point is the defect. Yeah, it's all good? Great. No problem. Sorry, Teti.
No, that's okay.
That one.
Thank you. Anything else?
Okay, so thank you very much, Théodosia, for this presentation. So you said we have a short break, isn't it?
Yeah, I think yes. And after that, we come back, and Dawn is going to actually show you some action, some live action from the lab, and he's going to take over to present his stuff.
Okay, so it's 10 past 3, so we come back at 15 or 15 past 3. Yeah, is it okay like that? Okay, thank you. So 5 minutes break.
Hello. Should we start back up, Tati? Okay. Hello, everyone. Hopefully you can see me. My name is Don. I'm one of the researchers at Strathclyde, and I'm just going to give you a tour of the lab.
Okay, so can we check Marius and Luigi, are you recording? Marius, Luigi, are you there? Okay, cool. Thank you very much.
Okay. So this is the outside of the main lab. You can see one big robot there and a few more over there. And then we go into the laser lab, which is over here. Teti showed you a slide or two about the robot system, and I've got a few slides that I can go over. We've taken off some of the lasers right now, but essentially we have our lasers on here, and then we can inspect quite big, quite complex samples. So you can see here, this is a very complicated kind of H-shaped sample that we have here. So this is majority of our robo laser system. And then to the left of that is our tabletop system, which I'll show you just now. So this is our main tabletop system. Here we have our generation laser, which goes through a couple of mirrors. And then Teti explained how we use galvo mirrors to steer it. So the generation IR laser comes out of there, and we can steer that left and right, up and down on our sample here. This here is our detection laser. This is actually just the front of the detection laser. It's connected using an optical fiber, which goes to the big, that's where the interferometer and all the optics are. So an optical fiber to the head of our detection laser. That again can move left and right, up and down. And right now, this is a relatively new setup. We are reflecting that off of a dichroic mirror onto our sample. This dichroic mirror methodology is relatively new, and that's what we are using on the robot system and on this system. And before I sit down and go to the presentation, are there any questions? Just about what you've seen so far, some quick ones.
Yes, how do you manage to, let's say, find the correct angle to hit your material, your specimen?
So we try to start off at least with the IR laser at 90 degrees. And then we use irises kind of here and here to figure out what that straight line is. Then this is, because it's bolted to the table, it's fixed. So it can only go at 90 or 0 degrees. And once we fix that, then we can adjust the mirror to make sure the reflected beam is also, so the IR beam and the green beam are both aligned. Does that answer the question? Is that what your question was?
Yes, yes.
Yeah,
thank you, Don.
No problem. So I'm just moving back to my computer and I'll swap cameras. So you should be able to see me from a different screen now. And I'll just jump into my presentation now. Does that look okay to everybody? Yeah.
Yes.
Okay, so this is kind of the core part of the presentation, and I'll be talking about rapid defect detection across large areas, but I'll also go over a little bit of the SMC methodology that Teti mentioned at the start of her talk. Firstly, this is what you just saw a minute ago, if you like, the robot system. So we have an IR laser. I showed you the galvo mirror, and the robot system has a much smaller dichroic than you just saw on the tabletop system, but the principles are essentially the same. The green laser is turned by 90 degrees, and the IR laser goes straight through. And just an overlay of what the lasers would have looked like if they were there. So there's the big generation laser and the same detection laser head on the robot system. And I've got a quick video of that system working. So this is what I meant by the flexibility. I'll just go back and run that again. We can move the lasers anywhere we want using the robots, which gives us a lot of flexibility on what kind of samples we can inspect, complex geometries, curved surfaces, pipes. There's a lot of possibilities that we can explore there. Relatively quickly, this is the next version that we'd like to build, where we're shrinking everything by half. And then this is the kind of third version, which we're trying to make it as small as we can do it with the resources we have. And hopefully then we can take this further and make it even smaller and have more of a kind of commercial product available. That's really a quick run through RoboLeaper. And next, I'll just go back to what Teti was talking about selective matrix capture. And the way this methodology works is it's a two-stage methodology. You have stage one, where you use sparse arrays to figure out what's going on in your imaging region. Then you have a decision-making process. You identify some regions of interest. Then you move on to stage two, use an optimized array and image that area, and you can start to classify defects. And what we've done is we've automated this entire process. And what I'll do is I'll just show you a quick video of all of this happening in 3 minutes now. So what's happening is on the top right, you can see the laser going through. And what we're doing is stage one. We're using sparse arrays to image that area. First, we used 3 elements. We don't see anything. We used 5 elements. We still don't really see anything. This is the noise distribution from the images that are coming up. Now we're moving on to 11 elements. So that takes a bit longer, and then we'll see what happens. So at 11 elements, there's something interesting, and there's a shift in the noise curve. So we use this to make a decision that there's something interesting in that image. Then we do some quick image processing, locate the image, and then this is where Teti was showing you, and there was questions about optimal element positioning. So we've positioned our elements now in optimal locations to image this defect. I'm just going to skip forward just to save time. But all of this happens, you can see a timer here. All of this happens in about 3 minutes, where then using the optimal array, we can then image that defect. Now, just for context, when we started this process, we didn't know where the defect was, but now we've found where the defect is, come up with an optimal array, and use that to image this defect. So that was a very quick kind of run through of how we've automated the SMC process. A lot of the work I've been doing since then is to come up with a more robust methodology for stage one and implement that stage one for a relatively large area inspection. So this is an example of a sample, which I would say is relatively large. This sample is about 30, maybe 40 centimeters long. One way to do it is image it using one large array, but that will take a lot of time and a lot of processing. So instead, another way to do it is image it using multiple small arrays. And this is what we'd like to go towards. But then the question is, how many elements do you use in the small arrays? What's your detection threshold for a defect using the small arrays? And the next few slides try to answer that question. So what we did was we used a large array, but not covering the entire sample. This is just a chosen region of the sample that we imaged using a large array. We use 400 plus elements, which is far too many elements. We'd never use this many elements. 85 mil aperture, 0.2 mil pitch. With that data, we were trying to image this 1.2 mil diameter hole that's about 13 mil below the first surface. And we can see that, but that's not the point of that data set. The point of that data set is we can subsample that array using much smaller arrays, so 112 elements, and have about 300 arrays. So what we've done is we've taken this large array, subsampled it, and come up with 300 plus small arrays. And that's where it gets interesting. We took that 300 plus small arrays and downsampled that even further. So like you saw in that quick video, we just used 7 elements, looked at the image, looked at the noise curve, and we can't really see anything of interest. Increase the elements to 14, still there's nothing really interesting in the image or in the noise curve. 28, not much. Then when we get to about 58 elements, then we start to see there's a defect appear and the noise curve shifts. Now this is important because in the next few slides, we go into a lot, we do this very quickly. So what I've done is this black line here is the minus 25 dB threshold. I've set a threshold and I use the fact that the curve shifts past that threshold to tell my MATLAB that I have a defect there. And this methodology is carried throughout this presentation. And just for completeness, that's the 112 element dense array. And you can see the noise curve shifts anymore, a bit more, and the defect becomes brighter. So now what I'm doing is I'm going through those noise curves really quickly but also I'm moving the array across the sample. So right now there's no defect, but as the defect comes in, you can start to see how this noise curve shifts. And then if I introduce a threshold, you can start to see how as the noise curve shifts past the threshold, I can use that as a detection, a criteria for detection if there's a defect or not. So this threshold now, where do I put this threshold? That's the next question you could ask. So then what we've done is we vary that threshold. So what you're seeing here is each vertical line was one kind of segment of the animation before, where we go 7, 14, 28, 56, 112 elements. And then as you move horizontally, is that array moving horizontally? So from left to right, this is where that 300 plus number of elements comes, 300 plus number of arrays comes into play. So from left to right, we have over 300 arrays. Then just taking this 28 element array as an example, you can see down here where the orange line is the ground truth. We have some false positives, but then where we should detect the defect, we also have some false negatives. So then the question comes, well, what's the correct threshold? Because right now I'm just using a 20 dB threshold. So this next animation is I'm changing the threshold as I go. So it's 13, 14, and you can see as the threshold goes up, the false positive goes down. But then if the threshold is too high, we don't detect the defect at all. So there's a range there that we could use. And what we've done is processed every 1 dB increment and try to figure out what the optimal threshold is that we should use. What I've done is then tried to present that data here, where what you're seeing is each line is different numbers of elements. Now, hopefully it's relatively self-explanatory that using less elements is faster. Because we're using lasers, we need to move them individually. So ideally, I'd like to do my inspection with 7 elements, if not 14, if not 28. I'd rather not use 112 elements. Then here you can see me changing the detection threshold. And you can see as the threshold goes up, my probability of detection decreases. So actually 7 elements and 14 elements isn't very useful, whereas 28 elements seems to be a good compromise. And let's just keep that in mind. Then let's talk about the false positive rate. So the false positive rate for all the arrays has a similar trend in that as you increase the dB threshold, it drops off slowly. So now the question is, okay, what dB threshold do I use? And at this point, you'd probably go back to industry and ask somebody from industry, well, what probability of detection and false positive rate do you want? And that's where these numbers come in. So this is the exact same numbers as this graph, just visual representation. And say, for example, industry tells you, well, we prefer a probability of detection of greater than 50%. And what we would like is a false positive rate of less than 18%. Then we can start to identify a point like this on the graph, where we use a minus 20 dB threshold and 28 elements, and that satisfies the criteria that industry gave us. This means that now we have, for the chocolate bars I showed you earlier, the number of elements we want to use and the detection threshold that dB threshold that we should use. Exactly the same information presented slightly differently. So this is the window that industry gave us, where they want a POD of greater than 50% and a false positive rate of less than 20%. And this is the point we found. So then using those numbers for a 1.2 mil defect, 13 mil deep, we can then come up with this optimal array. And the next step that we would like to do is using that optimal array, try and move it across the entire sample, locate the defect. And then if you remember early on in my talk, I showed you the optimized stage 2 array. Then we can try and image defects in large area, large samples. So it's a relatively quick run through of what I've been working on. I think that's everything I've got. So if you've got any questions, I'll be happy to answer them now.
Thank you very much.
Yes, Don, I have a question.
Yeah.
So I'm interested in a very similar, conceptually similar topic, which is sensor error detection or error detection in the data of the sensor. So still
Yeah.
kind of the bigger scope of anomaly detection. So I was wondering if you could go back to the, let's say, results table of before. Yeah, like the downside of using 56 elements compared to 28, it's really that big that you prefer to have.
It's just time. So this is probably not a good. I've got another slide. There we go. So it's just to do with time. So if we use 28 elements, it's 40 seconds
Okay.
per array, and depends how big or how long your sample is. That 40 seconds is then multiplied by however many arrays you need, and whereas 56 is, is it 4 times long?
Yeah, 4 times, yes.
Yeah. So that's really the incentive to
Yeah,
use
that's
less
the
elements.
trade-off. Okay, I understand. Because the element was the total length was 40 centimeters, 30, 40 centimeters. I got a bit lost with the chocolate bars.
Yeah, so the whole sample, I've actually got it with me in the lab. The whole sample is about 30 centimeters. Just 1 second.
Yeah, it's okay.
It's probably more than 30 centimeters, if you can see that. And then this is a 30 centimeter ruler. I don't know if that's the red bit is the ruler, so it's just.
Can't see you, Don.
We can't see you.
Oh, is my video not showing?
No,
Let me stop sharing.
we couldn't see you even when you were not
Can
sharing.
you see me now?
No, it still says Dawn Mobile.
Oh, but it's the other person. 1 second. Okay.
Yeah, now we can see your keyboard.
Here you go. So that's the sample, and it's longer than 30 centimeters because that's a 30 centimeter ruler.
Yeah. Okay,
So
understand.
it's relatively big, and it's, if you like, so that's a smaller ruler. And what we'd like to do is kind of go array, and then find what defects are in here.
Okay.
Any other questions? Nope. I've forgotten who goes next. I think it's Pete or Matthew. You can pass on to them.
So thank you very much.
Hi everyone. Just give me a second. I'm going to try to share the presentation. Okay, can you see it?
Yes.
Okay, so my part of the presentation will be about beamforming with 2D laser-induced phased arrays. So just a quick overview. Initially, I'll talk about 3D imaging with LIPAs, like what we can do and why do it. Then I'll talk a little bit about element localization of the generation and detection lasers. Then I'll talk about the basics of ultrasonic beamforming and laser ultrasound. Then I'll talk about some of the design strategies that we've been using. This has been kind of partially touched upon by Teti. And after that, I'll talk about the case study to show this with experimental conditions and results. And then finally, I'll summarize the presentation. So 3D imaging is very, very useful. And if we're using LIPAs, we can also do this completely non-contact for all the applications that Teti has already mentioned. And this is very good if you want to get a perspective of where your defects are. So you can really see, in this case, where we're imaging a sample with 4 bottom drilled holes, you can really see where they are relative to each other. And this is also a very important tool if you want to look at defects that are maybe a bit more complex, so you can get a very representative view of it compared to what you would get with a 2D image, which might provide a less accurate view of what is inside the sample. This also enables us to look at a bit more, so we can also extract slices, and it can just very quickly allow us to show what is in our sample. But one of the problems when we start doing 3D imaging with LIPAs is the fact that if there are some inaccuracies, you might have some problems with your scanning. So in this case, we're trying to do scanning in a straight vertical line, but you can see that if there is something off in the right video, you will see that it did not, the green beam did not go along the red line. It started kind of going diagonally. So this can happen due to quite a few different reasons. So if you have a non-flat surface and you're not aware of it, so you're not correcting for it, this can cause this inaccuracy. Or if you have some kind of misalignment in your system, or just simply if you have an error in your code that calculates the positions for your lasers. And of course, ideally, you would want to improve your system, so you remove all these inaccuracies, but sometimes you might not be aware of all the factors that cause this. So instead of going down that route, we are always trying to improve the system, but we also developed another approach where instead of finding the perfectly ideal positions, we are trying to find the inaccuracies of the system after scanning, and then we can correct for the inaccuracies in data processing. But it is to say that this doesn't always happen, just in case this occurs. So this would be if you have a 2D phased array, like what's on the left, where you have the same layout for generation and detection, ideally that's what you would achieve. But if you have some inaccuracies, so for example, if your generation elements will be more spaced out without you realizing it, you will get what's on the right-hand side. And this is actually very, very important that if you do have this inaccuracy, you should be aware of this, because if the elements are not where you thought they were, then your image processing code will not work accurately and you will get wrong images. So to overcome this problem, we've developed this method where for this method, we assume that we do know the accurate positions for one of the arrays, either for the detection or the generation array. So in this case, this example shows that you know your detection positions. So you use a single generation position shown by the red circle, and then you scan at all the detection positions. After you capture all the data for this one generation position, you do the TFM algorithm that Teti talked about, but rather than imaging inside the sample, you're imaging on the surface. So when you do this, you essentially image where your source was, so where your generation position was. And this is the image that you see on the right side. So the red dot shows where the source was. So when we get this image, we can look at the center of the red spot on the image, and that will tell us where the generation point is. And then we do this for each generation element. And then once we've extracted this position for each generation element, we essentially have the layout now after we have done the scan for the generation array. So we have tried this experimentally. For this experiment, we use an aluminum sample with 4 bottom drilled holes, and they were at different depths. You can see it on the figure on the bottom. This is a figure to scale, so what you see there is what was actually in the sample, so it's like the right depth. So for the experiment, we scanned the detection array with a pitch of 0.5 millimeter, and the generation array, we intentionally offset the pitch of this to be 0.625 millimeters. And this was essentially the artificially induced inaccurate positioning. So we're kind of assuming that we don't know where our generation elements are. We hope it is at 0.5 millimeter pitch, but it's probably not. And in this case, we do know it's not. So on the right-hand side, you can see the results from the element position locating part. So the blue crosses show the expected positions if it was 0.5 millimeter pitch, and then the red crosses show the position after we introduce this inaccurate 0.625 millimeter pitch. So when we ran the algorithm that I just explained in the last slide, we got the red circles on the figure, and you can see that it relatively well aligns with the red crosses. So it shows that we can see this sort of inaccuracy, even if we assume that we have no idea what the pitch is. So the black circles are fully calculated without any knowledge, but it can still find it. You can see that there is some very little misalignment, but this could also be to the fact that maybe our generation elements were not where we thought. So it is possible that the black circles are more accurate, except for a few extreme cases, but we have not tested yet, and this will be an extra step that we will try to do in the future. So after we extracted the black circle positions, we could do the imaging process. So on the left-hand side, the left column, you can see the images that we produced when we assumed a pitch of 0.5 millimeters. So this is when we didn't know our inaccuracies. And then on the right-hand side, you can see what happens after we do the correction. And then the top column, top row shows the images produced with shear waves, and the bottom row shows the images produced with longitudinal waves. And you can see that without the correction, we basically get such noisy images that you can't see anything on them. And after we do the correction, we can accurately see those 4 bottom drilled holes that existed in the sample, and we can even see the back wall. So after we are able to find our element locations accurately, let's move on to a more fundamental problem of 3D imaging. So it has been discussed before today that one of the challenges of LIPA is the really long data acquisition times that we need, and that also the simplest way to speed this up is to reduce the number of elements that we have. But again, as has been described before, this can introduce grating lobes, and then that introduces artifacts. So at some point, you will not be able to create images. So unlike in the previous case where we can see our defect very nicely, once we have the grating lobe artifacts, the image becomes uninterpretable. So this is just what Tete talked about before, so I will not go into detail with this. But our interest was how can we achieve efficient remote 3D imaging without introducing grating lobes. So before I go more into what we did, I want to do a little bit of a background on beamforming. So as some of you might be familiar with this, if you have a phase delay, you can do steering, focusing, and all sorts of things. And once you know the phase delays that you apply to each element to achieve the different phasing in the sample, you can actually simulate the response. So this equation here enables you to calculate what acoustic field you will have when you apply a certain delay law to your phase delay. The delay law is being the different delays to the different elements. So this is one example image of a simulated acoustic field that you can produce when you're focusing at that low red dot here that you can see. So that's your focal point, but you can see other features as well. And for this, it can help when you're extracting your data along this dashed red semicircle. So this can really show you where your side lobes are, where your main lobe is, what the width of the main lobe is, and how strong your grating lobes are if you have grating lobes. So this is a very effective tool of predicting the performance of a phased array when you're trying to design one. So you don't have to test each phased array. You can just quickly simulate it, and it gives you some idea of how good a certain phased array is. So this, what I just showed here, this model is a generalized model for focusing with a phased array. So this is not specific to, say, lasers or transducers, but if you start using your own specific array, you have to make it more specialized. So in the case of laser ultrasonic arrays, on the top, you can see an omnidirectional source or receiver, because these images are just focusing either in transmission or reception, but you can combine them together as well, which is what the total focusing method is doing. So if you want to consider the directivity patterns that Teti was showing before, on the left-hand side for generation and on the right-hand side for detection, you can get focusing with laser generation and focusing with laser detection. So these are the bottom figures. And then when you do TFM, you would just combine these two to estimate the acoustic field that you would have when you're focusing in both. So the phased array designs that we've explored to improve acquisition speed is going from periodic array to first going to non-periodic, a non-periodic random array. And in this case, because the array is no longer periodic, the grating lobes are spread out over the array directivity. So rather than having highly focused grating lobes at certain angles, they're spread out and they get generally weaker. The other approach we've tried is going from having the same layout for generation and detection, where the grating lobes would appear at the same angles when you're focusing in generation and when you're focusing in detection. So this array directivity here shows, the red line shows your array directivity in generation. The green is the directivity in detection, and the array directivity. And you can see that the grating lobes appear at the same angle, and when you combine them, which happens in TFM, the grating lobes remain with relatively high amplitude. Then when we go to what we call Vernier arrays, where the generation array has a different pitch to the detection array, the grating lobes appear at different angles because their location is defined by the periodicity. So the generation array might have a smaller pitch, and that shifts the grating lobe, compared to the detection array, which has a larger pitch and will again shift the grating lobe in the other direction. So when we combine these two focusing in the total focusing method, they don't appear at the same angle, so they cancel out. So in our case study, to show these optimized 2D arrays, we used this aluminum sample with a bottom drilled hole with 1 millimeter diameter, and this was 5 millimeter deep from the inspection surface. So you can see with the white dash square, here is where our array was synthesized. And it was from this array that the defect was 5 millimeters deep. And then the back wall was 20 millimeter deep. So we used the three arrays, the matrix array, where it was the same generation, same detection layout, and it's periodic. The Vernier array, where it is periodic, but generation and detection have different layouts. And the random array, where the elements are located randomly within some limits. But the main design parameter was that all arrays should acquire roughly the same number of signals, meaning that they take the same amount of time to scan. And these are the array directivities that we achieve for these arrays. So these are now, compared to the previous case, these are now three-dimensional, where color is the third dimension. And you can see that with the matrix array, when we're focusing at the center of our array directivity, we have very strong grating lobes around it. And then when we go to the Vernier array, these get much weaker. And then the random array does even better. So when we look at the peak amplitude of these, we can see that the matrix array actually has stronger grating lobes than it does main lobes. And then the Vernier array significantly improves this by reducing the peak grating lobe levels. And then the random array goes down to minus 12 dB compared to the main lobe. And then experimentally, we also see the same trend where the matrix array has these really strong artifacts. And it can see the defect with the red dash circle here at 5 millimeters, but there's just so many artifacts. If you were just looking at the image, it would practically be impossible to see what is a defect and what's not a defect. When we look at the Vernier array's image, it does much better. It significantly reduces the artifacts. There are still some artifacts, but it does much better. And then finally, the random array does significantly better. You cannot see any artifacts, and all of this reflects in the SNR values as well. So we can really see that the Verneuil array achieves better SNR than the matrix array, and then the random array gives the best SNR value. So just to summarize, we've looked into different 2D phase array designs for LIPAs, which are very efficient at just making these designs because they are completely reconfigurable. And we did show that we were able to considerably reduce artifact levels in the images. And this should enable us to go to faster acquisition without introducing these grating lobes and the associated artifacts. So that was my presentation, and I'm happy to take any questions. There's any.
Thank you very much. So, Jasmine, you have a question about sparse sampling or comments? Or a question maybe to other explanation?
But I need to think about some question because I think there is a relevant topic between me and what they are doing.
I don't know, can you hear Jasmine?
Sorry, the audio quality is not the best on my side. I'm kind of struggling to hear.
Okay, hello, I'm Jasmine.
Sorry?
I'm working on compressed sensing, and I think my work is a little bit related to what are you doing, because we are also working with ultrasonic signals in the sparsity in the full matrix sculptures. We're doing the same stuff almost, but I wonder which, like, for the performance evaluation, which matrix is that you are using?
For the image evaluation, did you say? Sorry.
Yes, for the defect detections, which performance metric evaluation are you using?
So in this case,
Is it not noise ratio only, or according to what you're measuring the performance evaluation? For the imaging and for defect detection?
so did you say crack detection? Oh.
What you want to detect?
The defect detection.
Defects.
Crack detection. Yes. So in this specific case, the parameter that we were looking at was relatively simple, just looking at SNR, because in our case, we're assuming that the only defect we have is that the one. I'll just show the screen again. So we're not specifically looking at defect detection. We're assuming that, so this is our defect, and everything else is noise introduced by grating lobes, like artifacts. And then basically, if you just look at the level of the artifacts compared to our defects, the signal, we can kind of measure how much grating lobes we have, how much artifacts we have, if that answers the question.
Okay, and are you considering the medium to be homogeneous medium? Are you ignoring the multiple scatter?
Yes, exactly. So this is assuming that we're not able to image like grains themselves. So we're ignoring, like, the artifacts are so much stronger than the noise we get, like coherent noise we get off of the structure. Whereas I'm guessing maybe in your case, you're not worried about grating lobes as much. You would be looking at coherent noise?
No.
No?
What are you going to look at? Are you going to look at coherent noise, like scattering? Or?
No, we are also ignoring it.
So
Thank you so much for your presentation. It is so relevant to my work. I think I can later just like send you some emails or something like that.
yes, sounds good.
So, Jasmine, you started your PhD. When did you start your PhD?
Last October.
Last October, and she's working in Fraunhofer Institute in Illinois, in Germany.
Okay. If you would like to get in touch and we could talk, I'm happy to.
Yeah, that's gonna be great.
Are you using laser ultrasound as well?
Are you using laser?
No, we are not using laser, but I think one of our colleagues is using it, but I'm not working on laser. But my PhD topic is to apply contrast sensing using different applications. So I'm investigating different applications as well.
I think you have been working with Alina, who invited you, Théodosia, but Alina is on a sick leave, and you have been using an array, no? Trying to optimize an array, but it was on concrete with
Yes.
multiple source, multiple receiver, a traditional, a sensor for concrete investigation, and you are trying to optimize it somehow, or you have the objective?
So Alina's data was ultrasonic data, was measured from concrete and polymer, and it was in a full matrix capture mode.
Yes.
And it was collected with Mira transducers. And we are working to apply some dictionary learning to minimize the data size for
So
transfer.
it's very similar.
Yeah.
So you have to, yes, look at your colleagues' work. Okay, thank you.
Sounds very interesting.
Yeah, Charles.
I have a question for Teddy. Yeah, because I'm writing still art recently, so I'm considering if it's possible to write your technology inside my paper or not, because I think configuration of the measurement is very interesting for me. It's a part of like interferometry technology for optical measurement. So is it possible to like provide some schematics of the layout?
Yes, these have been already published. You can find them in our published papers. And you are more than welcome to cite us, or anyone who is welcome to cite us.
Okay, yeah.
So yes, do not hesitate to send this information to our doctoral candidates, and I think that the 11 doctoral candidates we have will be interested.
Should we move on to Matthew's presentation? I'm conscious of the time.
So thank you very much again.
I too am conscious of time. Hello, everyone. And hello, Teddy and chair of the meeting. I have roughly 25 minutes more content. I can move fast. I appreciate this. There's 14:58 here in the UK. I guess it is 4 o'clock for you in Europe. What do you think? Maybe the interested people can remain in the meeting. I'm very happy to run for my full prepared material. What do you propose?
For me, you can go for it.
Yeah, I have no conflict of time.
Absolutely.
Okay.
I will begin. I will not be offended if you cannot stay beyond the scheduled time for the meeting. So please, I understand. And thank you if you do stay. For it's a pleasure to present work, and it's contributing to all the same themes you have seen this afternoon: the laser ultrasound technology, and some more problems that we face and solutions to those problems. So I will end my presentation. Do you see the start of my PowerPoint? Is it okay? I'm afraid I no longer see you, so I may have to have a audio confirmation.
All
Yes,
good.
it's not
All good?
Yes, good.
Excellent.
Yes.
Thank you very much. Okay, so the first set of slides you will notice from the list of authors here at the bottom. I will just use a laser pointer as well. I am not the author of these slides. Gio Davis is a postdoctoral researcher in our group, in Teti's group, and he unfortunately cannot be here today, but we would like, and I will present on his behalf, his recent work on surface acoustic wave suppression for bulk wave imaging of near-surface defects with an application to additively manufactured components. And it's all using our laser-induced phased array technology. So in this work, we are suppressing part of the signal which we do not have an interest in. This is the surface waves. When we're in an application where we're trying to make the most of the relatively weak, relatively quiet bulk waves, which are going downwards into the bulk of the sample to investigate subsurface defects, we no longer care about the surface waves, so we want to filter them out. So this is the global theme of this talk. So all of this work and the slides are prepared by Gio Davis. So I'll just preface that at the start. So what is the problem? Why do we have to expend energy to filter out the surface acoustic waves? Well, I hope to illustrate the problem to you here. Here we have a sample. This is a block of aluminium with some side drilled holes in it. You've already seen similar samples in the talks of this seminar. If we scan a laser ultrasound phased array on the surface of this sample, and we attempt to do a total focusing method, so full matrix capture, total focusing method, subsurface image of the sample, we can create a lovely TFM image. And you can hopefully correlate the locations of these indications in the image, the colorful spots, with the true locations of the defects that were present in this sample. And so this is very nice. This sample has 5 holes in it, and we resolve 5 holes. But what else is a strong feature in this image? It is this semicircular area of high amplitude close to and bounded by the extremes of the phased array aperture. It's an artifact, and it's introduced by the presence of the surface acoustic wave. Now, in this sample, it doesn't necessarily cause a problem because it is remote from the regions of the image where we have interesting defects and interesting signals. However, if you think of an alternative sample where you have defects close to the surface of your sample, close to bounded by the array aperture, then this sample, this artifact might start to be a problem. And I say it is due to the surface acoustic wave. I will come back to a more detailed reason as to why this artifact forms. But you see here just some introductory figures that show an example of one of our A scans. So this is a plot of amplitude over time recorded by the detection laser. This is the raw data. This is the format that the raw data comes from our hardware. And you can see this very large perturbation in the data. This is the surface acoustic wave signal. And so you can see how much larger that it is compared to the rest of our A scan. And this is one of the main reasons why this artifact is such a problem. It's because the surface acoustic wave is very loud relative to our quiet signals from the deep, from the bulk. The artifact also forms in the place that it forms and with the shape that it forms because of the total focusing method imaging algorithm, which is the algorithm that converts these raw A scans to an image. So it transforms from the time domain, amplitude over time, to the space domain through knowledge of the ultrasonic speed and the equation speed is equal to distance over time. So if you program in the speed of sound for your material and for the wave mode that you want to image with, here aluminium, speed of sound, shear wave around 3,000 meters per second, you can convert your time domain signals to a space domain signal via the total focusing method imaging algorithm. And part of this algorithm is also why you see this artifact. So this will all be explained as I proceed. As I mentioned at the start, the reason why you would care to remove your SAW signals and from your images as well is that for a given sample, if you have an array of a given size and some defects in your sample that you want to image, or that you may not know if they are there, the geometric artifact from the surface acoustic waves, the crosstalk as we call it, provides a semicircular blind zone which may blind you to certain defects that are close to the surface and bounded by the aperture of the array. It does not matter the true dimensions of this sample. It's a geometrical artifact, and it's based on the width of the array versus the depth. So this could be kilometers for all you want to say. The surface acoustic wave will still produce these crosstalk signals. So we're interested in removing them to see the defects underneath this blind zone. I hope that is clear. Specifically, GEO has been investigating an application to additive manufacturing. This is a diagram of a additive manufacturing process whereby metal is deposited in layers to build up a component. And for this particular process, and for many different additive manufacturing processes, you may obtain defects that are close to the surface and that are bounded by the apertures of arrays that you would use to scan such a sample if you were using laser ultrasound arrays. So this is the particular application that this could be useful to. So this is another TFM image that you see here on the left. And it's the problem that I've been describing about a geometric artifact obscuring a defect. Now you may, with your human eyes, which are very good at detecting patterns, you can see that there is maybe something going on here where I am pointing with the laser pointer. However, the amplitude variation relative to the noise, the signal to noise ratio, or the signal to crosstalk ratio, is not very high. So it's not very clear what is happening here. And we would rather, if a defect is present, that was a clear signal relative to a suppressed, a background that is, in this case, dark blue, nice and clear relative to the signal. And the reason this is happening is because the surface wave signals are being summed to those pixels in the TFM imaging domain that are also the same pixels where you are summing your shear wave, your bulk shear wave responses. There's a video now playing on your screens, hopefully. It may be quite jumpy. I've paused it a little bit. This is our full data set. This is the full matrix of A-scan signals, and I'm playing it through in time. You don't really need to know more than that. This is just all of the raw data that we have. And it's this time domain data that we convert to the space domain through knowledge of the ultrasonic wave speed. You may also see the X's, little crosses that they may flash for you. An apology if it's not very clear, but you should be able to see black crosses, maybe gray crosses, they're quite faint, and then lastly white crosses. I'll play it again, so you hopefully look for those. Those crosses are marking the points in the time domain signals which are sampled by the imaging algorithm to be summed to the pixels which are annotated with the corresponding colors here in the space domain. So the total amplitude value that appears at the pixel, which is white here at these array coordinates, this white pixel is determined by the white crosses that you will see towards the end of the video, which appear in a sort of circular pattern that radiates outwards. So all of the amplitude values that sit at those white points with the white crosses on them, they get summed. That's the delay and sum algorithm. They get summed and pasted to the pixel in the TFM image that you see there with the white point. Likewise, the other colors are shown by the corresponding colors in the crosses in the video. So the black crosses, you can see, they overlap strongly with a very bright yellow and blue feature, which is two parallel lines which move outwards from the diagonal of the data set. The blue and yellow, the very high amplitude feature with the parallel lines, that's the surface acoustic wave. And you can see that because the black crosses are sampling that wave, that is what leads to the very loud amplitude in the space domain at that black pixel here at the surface. And likewise, the gray colors are not coming up very well, so it may not be so clear, but between the white and the black, you can see there's varying amounts of overlap between the sampled points and the surface acoustic wave. So that's just trying to give you a sense of how the imaging algorithm interferes with the surface wave and why it's localized to the surface. You see that the white crosses appear later in the video, and they do not overlap with the wave. They chase it, they sort of nearly get to it, but within the aperture of the array, they do not overlap with it. So that's why the SAW crosstalk runs out after a certain point. SAW crosstalk is unique, really. It's worst, I should say, for the particular wave mode, which is TT. That is when you image with a transverse wave, a shear wave, transverse wave, on your way down, and a reflected transverse wave as it comes back up from anything that is reflected. And this is much slower than your longitudinal wave. Your longitudinal wave is very fast. Aluminium, it's about 6,000 meters per second. You can see some velocities here. The transverse wave is down at 3,000 meters per second, so half the velocity. Crucially, the speed of the transverse wave is only slightly faster than the speed of the surface acoustic wave. And that leads to this geometric problem where the surface acoustic wave arrives at the same time as a bulk transverse wave that has gone down and back up to the surface. Even though the path length traveled by the surface wave is the straight line, whilst the shear wave travels along the hypotenuse, so a bit longer, because the shear wave in the bulk is slightly faster, just slightly faster, they actually arrive at the same time at the detection location. Okay, so the arrival is simultaneous. They are superimposed in our A scan. You have a loud surface acoustic wave with a small, quiet, additional perturbation from the bulk shear wave, and therefore you have this interference, and both will be summed to that pixel in the TFM image, and this is what creates the artifact. Ah, yes, this is just what I described with my voice. So the geometry of the hypotenuse, but then the slight change in the velocity, that the shear wave in the bulk is slightly faster. So even when it goes along the hypotenuse, it arrives at the same time. So I've explained to you the origin, hopefully, of the artifact. Now I present the methods that we use to suppress the surface acoustic wave and remove this artifact. A lot of them are quite mathematical, so I will not go into details. I'll just give you a catalog of them. And if they seem relevant to your work, maybe you can follow up and investigate them in your own time and investigate the details of them. This 6 TFM images that you see here, it starts in the top left corner here. This is the raw TFM image for this particular data set with no attempt to suppress the surface acoustic wave. And we have a defect that is present in the center of the array, and it's interfered with the artifact quite strongly, and therefore we would like to improve the contrast between the bulk defect and the surrounding defect-free material by filtering out the SAW. And we have five methods that we have applied separately to the data set to attempt to do suppression. And you can see they have varying effects on the degree of contrast, that is contrast improvement that we see. And I'll just go through them quite quickly. So the first very simple approach is amplitude thresholding. Those are two very long English words, but it's very simple. You just take your raw A scan and you limit the amplitude, and you say anything that exceeds this amplitude just sits at the amplitude. So you cut the signal in both positive amplitude and negative amplitude. This means that when you process the A scans with the same TFM imaging algorithm, rather than summing a very, very large amplitude value that is way higher than the normal amplitudes for the bulk waves, and therefore getting very bright regions in your image, you get a slightly lower value. And you can set your threshold based on optimization of your image quality. Okay, a very simple approach. This is a sort of first try, as it were. Second one, wow, this is quite a lot of diagrams here. I'll see if I can distill it to the simplest aspect of it. A mean waveform subtraction. This attempts to find in the full matrix of A scans, you noticed in the videos we saw earlier, there were parallel lines that radiated out from the diagonal of the full matrix. The reason the lines were parallel is because they corresponded to the offset subdiagonals of the matrix corresponds to sets of generation and detection elements with the same surface spacing captured throughout the array. And you can see them illustrated here. In full matrix capture, you capture every permutation of generation and detection point possible across this linear array. That's why this data matrix is a square, because it's every possible combination of I generate at position 1, I detect at position 14. I generate at position 2, I detect at position 16. So we have n squared A scans captured. And if you take sets of offset subdiagonals and you process them as one batch, you'll see that for that set of A scans that are along pairs of offset subdiagonals, the surface acoustic wave arrives at the same time. And the reason is because all of those A scans, even though they were from different positions along the array, the generation and detection laser were separated by the same amount on the surface. There's no other inhomogeneity, we assume, so the surface acoustic wave always arrives at the same time. So what you can do is take a mean through that batch of A scans where the surface acoustic wave, arrives at the same time, and the mean waveform will strongly preserve that feature, which is always at a consistent position in the whole batch. Likewise, any other surface waves, we have a shock wave that travels through the air when our laser fires, and that will also be preserved in your mean waveform, that is the mean of all of these scans. By contrast, the bulk waves, they travel along the hypotenuse paths, so they are, the echoes are due to a localized defect. So when you take pairs of scans with the same surface separation across the array, the bulk waves bouncing off that defect will not arrive at the same time for all of those scans. And you may not be able to see it, it might be quite faint, but I've represented this with a hyperbola here. Generally, for point defects, you see hyperbolic patterns of arrival times as a function of array position. And therefore, when you average down through this stack of A scans to create a mean waveform, the incoherent hyperbolic arrivals are not preserved in the mean waveform. They are averaged out. Okay, so now we have a mean waveform which just contains the surface wave features, and we can go back and subtract that mean waveform from all of the A scans in the batch. And hopefully what that does is eliminate selectively the surface waves and preserve the bulk waves. And you'd have something more like this, a nice strong hyperbola, because the surface waves have been suppressed. Okay, so we call this mean waveform subtraction, and it suppresses quite effectively the surface waves. As an extension of mean waveform subtraction, you can do more maths, and you can first apply mean waveform subtraction, and then this may suppress 80% of your surface acoustic wave signals. The last 20% that remains, even once you've subtracted the mean, is remaining variance in your data set. And this may be concentrated around the surface wave because it is so high amplitude. So if your surface waves are arriving at slightly different, very slightly different times across this patch, even though you expect it to be exactly the same time, they may be slightly offset, then you'll have residuals remaining in your data set even once you've subtracted the mean. So you can take this zero mean data and do principal component analysis on it, which is shown in the maths here, but what you need to, the takeaway is that the remaining variance in the data, even once you've subtracted the mean, will be concentrated around the location of the surface wave because it is so high amplitude relative to the other features. And even if you move it slightly across the A scans, the residuals will still be very extreme because you have these high gradient regions in the surface wave signal. Anyway, the principal components of variance, which are the eigenvectors of the covariance matrix, there we go, those principal components are waveforms. They have a waveform shape, and you can subtract those weighted with the correlation coefficient from each of your A scans in the batch. And that will mop up maybe the last 20% of the remaining surface acoustic wave signal, or 19%, it's never 100% effective. Moving onwards, another method is frequency wave number filtering. This is quite a mature method that I'm sure many of you will be familiar with from acoustics or even optics. You can perform a two-dimensional fast Fourier transform of your spatially sampled wave propagation data from the time domain. You apply your Fourier transform, you obtain frequency wave number plot, a 2D fast Fourier transform. And then in this domain, in this 2D Fourier domain, your different waves with different propagating speeds will be spatially separated as different features in your 2D Fourier plot. So then you can design a selective filter to suppress locally just the waves that you don't care about and preserve the waves that you are interested in. So the 2D FFT is a good way of obtaining a distributed description of all of the waves inside your data, and then you can apply filters, so a selective mask in this case, to just remove the highest amplitude feature for us, which is the surface wave, characterized by this diagonal X, as you see it. So we design an X-shaped filter, and then we just suppress everything that falls inside that X, and then we do the inverse Fourier transform to recreate our data, and that will have the surface wave suppressed to some degree. Lastly, phase coherence imaging. This is where you ignore the amplitude information in your signals, and you instead just look at instantaneous phase, which I believe you can obtain from the fast Fourier transform. So you convert your signals to a phase informator, phase data only, no longer caring about amplitude information, and then you perform imaging, and you develop a contrast-based imaging algorithm that will give you contrast based on the coherence of the phase values, the instantaneous phase values, across your signals for a given pixel. So you pick your pixel, you sample your time domain data, you get all of your time domain samples, you look at their phases, you can plot those on the phasor in imaginary axes, and you obtain contrast based on the degree to which those values are similar, cohered on the phasor. If they're very similar, like you see in this picture, you get a high contrast. And if they're very random across the phasor, you get a low amplitude. Sorry, a low amplitude. If they're coherent, you get a high amplitude. And then your imaging parameter is now your phase coherence rather than your delay and sum amplitude. The idea here is that bulk wave echoes will be coherent, and the surface wave signal, which was very high amplitude, but look here, we're not caring about amplitude, it's just the phase. It will be out of phase relative to those bulk wave echoes. And so it won't contribute greatly to this new mechanism of generating contrast in the image. So it will, your image is now less sensitive to these high amplitude surface waves, and it's only really looking at the phase cohered bulk wave responses. So just to present the final slide, this was the same slide I presented earlier. You can see the various effectivenesses of these different methods. Amplitude thresholding doing quite a nice job of getting rid of the extremes, but there's still quite an artifact. FK filtering, that was the 2D Fourier transform with the X-shaped filter. That's again doing a nice job. We've got slightly better contrast. Mean waveform subtraction, pretty good. You can see the residuals that I mentioned, which are then mocked up by the further step of principal component subtraction and giving a really nice quality image here. And then PCI, phase coherence imaging, a totally different imaging contrast parameter, but again, less sensitive to the surface wave here. Okay, if you would like further information, Gio's paper has been published, and you can see the title there, Near Surface Defect Detection in Additively Manufactured Components, Laser-Induced Phase Arrays, Surface Acoustic Wave Crosstalk Suppression. He details all of the methods that you see here as applied to our data. There's also multiple methods in geophysics, which I encourage you to investigate if you're interested in selective suppression of signals. Okay, so this was Gio's talk. I guess I can open up for questions there before I continue to my work.
Okay, thank you very much, Matthew. It was very didactic. I really enjoyed it.
Oh, thank you. Thank you very much.
Actually, I'm working with colleagues here in France on surface waves. So if you've got a filter, or if you can remove them, you can just then take them and work with them.
Yeah, exactly. From -1 to from 0 to 1.
Yeah, I found your explanation very clear. So thank you very much. So I don't know if you have questions or comments.
Looking at how I can see.
Is additive manufacturing 3D printing?
Sorry,
additive manufacturing, is it 3D printing? So this is the question?
Yeah,
absolutely.
Okay. Sorry, I was a little stupid.
No, it's a good question.
In the USES2 project, actually, when we set the proposal at the beginning, there was more PhD funding, and they changed in Eurozone Europe for 1 year. And there was a topic on additive manufacturing, because it's quite trendy, but unfortunately, we had the maximum, and it's 10 + 1 doctoral candidates. So this topic is not, we have no PhD students working on this, but it's very relevant.
Well, it's a very active area of research, especially in NDT.
Yes, yes. Mm-hmm. Okay, so
I'm not sure if there's even anyone left through. All I can see on my slides, but if you have further questions,
we have a question here.
Yeah.
I do have a question. So, among all the methods you propose, the principal component subtraction seems to perform best. I was wondering, and among also the other methods, because you have a very simple medium, it's a pretty much a homogeneous phase, there's a defect. But how transposable to more complex spaces are these methods? I mean, speaking about geophysics, we have gradients, we have heterogeneous. How can those surface wave filtering tricks be still applied in these less favorable cases?
More complex media. Yeah. So I think an example of. Oh.
Do you want to take? Do you want me to take this?
I have some thoughts, if it's okay.
Okay, sorry. Go.
Oh, but please, maybe add to Teti. I think there's nothing intrinsically. Oh no, I can start to see things. So one of the assumptions of, say, the mean waveform subtraction. Oh, if I can get back. As an example that I can speak on, I worked on this method, so I think it's the one that springs to my mind and the one that I'm best qualified to comment on. The assumption was that you have a isotropic and homogeneous material, and therefore, even if you take pairs of generation and detection elements, or A scans from generation and detection elements from different regions of the array, spatially different regions of the array, that the surface acoustic wave will always arrive at the same time because the sample is homogeneous. But you can imagine immediately that if you have a sample that is half aluminium and half copper, and yet you perform an array that straddles the boundary between the two, then at some points, if you perform this batching from the full matrix in the same way, you're assuming that they all arrive at the same time, then you'll have more of an error because of the inhomogeneity of your sample. So just as one example, I think that's a good example. How we can solve this. This batching is actually, it's a nice way to do it when you know the geometry of your array, but it's limited to periodic arrays. And you saw from the talks earlier, from Pete's work and from Teti's presentation, that we're actually interested in having more, well, not necessarily more complex, but a more different array designs where it's not necessarily geometric arrays of squares, but random patterns and or interesting tiling geometries or spirals or things like that. So what can we do when the geometry is different? We actually have developed a solution to that problem that is also applicable to the example you give of an inhomogeneous sample, which is rather than assuming that we obtain this alignment from the geometry of the array, we force the alignment by performing cross-correlation. So we cross-correlate all the traces, find the maximum in the cross-correlation, align all the traces based on the cross-correlation, and then apply the same method. So it obtains this same stack that's aligned, but from a different route. You're not just depending on the geometry of the array anymore, you're now forcing that alignment by applying a cross-correlation based method. So there are extensions to the methods that make them more applicable to, as you say, more complex scenarios. I hope this is a nice answer to your question. Well, I hope this captures some thoughts on what you asked.
Okay, thank you.
I also have to say that this is a very good solution, cross-correlation, but it's also it's an interesting question, because some of these methods that we have been using for surface acoustic wave suppression come directly from geophysics. For example, FK method for source suppression is a method that is used in geophysics. So my first response from the question was, wow, a person who is actually doing geophysics is coming back to laser ultrasonics, where we have been borrowing things. So it's good. It's a really good, and it showcases the power of this network, of this doctoral network that brings together the two communities.
I agree with you. Okay.
I have two general questions. Maybe it is connected to the previous presentation. Maybe it is standalone, but I wonder, how can you deal with the fact if they are so close to each other? And if a defect is coming from the back wall, how can you identify this is a defect, not a back wall reflection?
I can jump in on that. I think it may be applicable to Pete as well. So if Pete's still on the call, he can probably give you his thoughts as well. The question about, so if I've understood correctly, how can you deal with defects that are very close together spatially in the sample? So two, say, very small holes that you've located very, very close next to each other. And then separately, how can you locate and identify a defect that is close to the back wall, which will also give a very strong reflective response? So my thoughts on these two questions are, first, identifying defects that are very close together is, I suppose, the domain of having a array with a certain resolution criterion. For a given sampling of the wave field, which is the density of your array, you can perform calculations on something called the Rayleigh criterion, which is, I think, fundamental to optics or any kind of wave imaging, where you can perform mathematics to discern the minimal distance between two features where you can still separate them based on some amplitude criterion, such as 6 decibels, half of the amplitude. And then as they get closer than that, then the responses from the two defects will merge into one peak, and you can no longer sort of claim to have identified two separate features. I think this criterion can be considered in the design of your array. So if you know that you want to be able to see defects of this size, you can create a very densely sampled array, which is designed for having a very small wavelength. You can also filter the ultrasound to a higher frequency so that you're imaging with a smaller wavelength of wave. There we go. A smaller wavelength of wave, which gives you a tighter focus, just like an electron microscope versus an optical microscope. If you use a smaller wavelength, you can see smaller features. You can beat that diffraction limit. And then on the back wall, there might be differences in the scattering properties of the defect relative to the back wall that you can exploit to look at the defect selectively relative to the back wall. TFM tends to throw all of your information together on one plot, but you can take a few steps back and look at the fact that if you have, say, a circular defect or a curved defect amidst a back wall that is otherwise flat, your back wall will give what we call specular reflections, where the sound in is bounced off at an angle that is equal to the incidence angle, like snooker, whereas a more localized point defect with a more isotropic reflecting property will give reflections that return perhaps to the location from which the incident wave arrived. So you can use those differences in the physical responses of those two features, the back wall and the defect, to discern them slightly better. You can design an imaging algorithm that will create contrast based on this. So this is potentially one approach.
Okay, thank you.
Okay. So I think that after, I don't know, 2 hours and a half, everybody is silent. So do we have any question? Nani, okay.
Yes, by the way, could you, Pete, and Dawn please share your slides in the common area? Share the slides, yes.
Yeah, it would be nice to, if you can send the slide to, I think it was Alina who invited you, Théodosia, and it's, yes, or to any of the doctoral candidates, it will be very helpful. And we will ask you if we can to put the slides on our website and the link to the YouTube video. So, and if you say yes, it's okay. If you say no, okay, it's okay as well. And what else? So I really would like to warmly thank you again. It was very interesting, and you covered a lot of topics that are very relevant to specific PhDs that we are running now. And I guess that in the time, all our doctoral candidates who will go with deeper knowledge in the year to come, that nice discussion will take place. And by the way, Théodosia, you are invited. We have we are organizing, of course, there is this meeting in June where you can listen to our PhD students, and you're welcome if you want to come. It's covered by the project. And also in February, we are going to go in Madrid. And there is we have to organize a meeting with the external advisory board members there. So we hope that we will see you there. And thank you very much again for the presentation, and with all your colleagues as well. Thank you very much. Thank you.
Thank you for inviting us.
Thank you. And congratulations to all the doctoral candidates who have asked questions. I think it's important to learn to ask questions, and I think that almost all of you have asked questions, so it's good. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye.
Thank you, everyone. Have a nice weekend.
Bye.
Bye.
Thanks.
I'm going to end up on the call.